Okay, so I'm going to go ahead and start, Marshall.
Yep.
So I'm going to talk about a two-dimensional diffusion process. This is work that I'm doing with Barcott, our PhD student. Now, in the first part of the talk, I'm just going to review some things, basic things about Brownian motion, that is especially one-dimensional Brownian motion. With an emphasis on its local time, which is basically the time that it spends at a single point, a way of characterizing that. So then I'm going to basically take an integral kernel that has appeared in several recent articles, and I'm going to use that to define a probability transition kernel, probability transition function. And then I'm just going to study that process. I'm going to discuss the interesting properties of that process. And the main interesting factor is that unlike a two-dimensional Brownian motion, so this two-dimensional Markov process can visit the origin. Okay. All right. So skipped around. Okay, let me go back. I'm going to use my computer pad. All right, so let's start with the definition of an n-dimensional Brownian motion. So an Rn valued stochastic process is said to be an n-dimensional Brownian motion. First of all, if it has continuous sample paths. So if you fix any omega in the probability space, then the sample path, that is the function from time to the value of the Brownian motion, is continuous. So second is that given 2 times s and t, the increment of the process is independent of the past. In other words, it is independent, the bt minus bs, which is a random vector, is independent of the sigma algebra generated by the past of the Brownian motion up to time s. Okay, so third property is the distribution of those increments. For any s and t, the random vector bt minus bs, that is the increment of the Brownian motion, is a centered normal random variable with covariance matrix that is very simple. It is just the scalar t minus s multiplied by the identity matrix. So more explicitly, this normal just has the Gaussian density given right here. Okay, so it is just it is just the distribution with this Gaussian density. Okay, so we can express the second and third properties together just by writing that for any set E, the probability that the Brownian motion is in the set E at time t, conditioned on the information in the past up to time s, is just given by this integral of the Gaussian density function. Now you can read from this formula that this is the Brownian motion is a Markovian process with a very simple transition probability density function. So to go from time s to time t, you just have this Gaussian. You can see that it only depends on t minus s and x minus y. So that means it's homogeneous in time, so stationary, and it's also homogeneous in space, that is the independent increments. Now, to construct an n-dimensional Brownian motion from one-dimensional Brownian motions is extremely simple. So if you just take n independent one-dimensional Brownian motions, then you could just put them into a vector to construct an n-dimensional Brownian motion. So it's just that the components of an n-dimensional Brownian motion are just independent one-dimensional Brownian motions. Okay. So, let's see. So here are just sort of sample paths. So what do the Brownian motion trajectories look like? So they're just sort of, sort of wiggling around, and they have no sort of direction that they want to go. They're constantly sort of undercutting what they've done before. And so you can see that this is sort of a square root function. So they sort of, in some average sense, so stay around a square root function in their intensity. Okay, so this is roughly what they look like. So if we were to zoom in closer to, say, a single part of this Brownian motion trajectory, so it's local behavior. In other words, the appearance of it would be very much the same. So Brownian motion paths have sort of a fractal characteristic. If you zoom closer and closer into a Brownian motion trajectory, it just looks the same. Okay, you can't tell how close you're looking. Okay.
Hi, Jeremy. Can I have a question?
Oh yeah, sure.
So your n-dimensional Brownian motion, each dimension, different dimensions, they are basically independent, right?
Yeah, the component, that's what I was trying to say in the last slide, in this last point, point is that you can just build an n-dimensional Brownian motion from one-dimensional Brownian motion.
Yeah. So, yes.
Yeah.
So based on definition, your it's IN, right? Just the covariance matrix is just something in a previous slide.
Yeah.
And go back to.
Yeah.
So you have
this.
P minus IN, right? So that's the reason, right? Yes.
Yeah. So it's just the identity.
Just the
so
identity
it's trivial. Yeah. It's very trivial.
Yeah. So
That
it's different from
trivial,
like a Brownian sheet. Yes.
Mm-hmm.
Yeah.
Yeah. This is not like a Brownian sheet.
No.
Okay.
Yeah. I see. So it's just put a one-dimensional Brownian motion together. You have
Absolutely.
Yeah.
Absolutely.
Okay, I see.
Perfect. Way to say it. Yeah. But what I want to talk about in a moment is that the dimension does change the properties. Okay. But before we go there, let's just talk about something called Wiener measure. Okay, so let this denote the set of continuous functions from the time interval 0 infinity to Rn. Okay, so these, I want to call these paths. So there is a natural metric that you can apply to paths from 0 to infinity. Okay, you could construct it this way. You'll see this in any textbook. The details don't matter for us right now. And so one perspective on what a Brownian motion is you can think of it as sort of a random variable taking values as paths. So a more technical way of saying it, so it's a random sort of path valued element. Okay, so it's a path valued random variable. All right, so now if the initial position of the Brownian motion, it doesn't have, we might take it just the Brownian motion to start at 0, but it could just be some more general distributional measure. The initial position could be random. So if we do have some initial distribution, so the distributional measure P sub mu of the Brownian motion as a random path valued element is referred to Wiener measure. So Wiener measure, what does it refer to? It's the distributional measure of a Brownian motion as a random path valued element. Okay, so when we say Wiener measure, we're referring to sort of a distributional measure, but on the paths. Okay. So now I want to talk about a little bit about how Brownian motion does change from dimension to dimension. Okay, so as before, let B be an n-dimensional Brownian motion. Then for almost every sample path of the Brownian motion, we have the following behavior. So if you fix any point in space, we might as well just take this x to be 0. If you want to just say it's 0, fine. But if you pick any point and any large time, so time in the future, there exists some time after that time, so sometime following that, such that the Brownian motion will visit the point x. Okay, so what is this telling us? Telling us that the Brownian motion will perpetually return to every single spatial point. So it'll keep returning everywhere. Okay. Now let's jump now to compare this to dimension 3, which is quite different. Now, if you fix any bounded set, say an open ball with a very large radius, then there exists some time after which the Brownian motion is in the complement of that set, meaning that it's outside, and it will never return, okay? So this is regional transience, meaning that the Brownian motion is just gradually going to infinity in dimension 3. So it does not keep returning to local regions, say around the origin. Okay, so these two are both sort of easy to understand. So the one-dimensional case, the Brownian motion keeps returning perpetually to every single point. In the three-dimensional case, you have this regional transience. You just basically go off to infinity. Okay, it's random when you do that, but you will eventually go off to infinity. Okay, so what about dimension 2? That is the in-between case, the marginal case. So if you fix any point, again, we could just take this 0 to be 0, then the Brownian motion will not hit that specific point that you chose for me, ever. Okay, if you fix some point, say the origin, right? Then the Brownian motion will not visit the origin ever. Okay, so it's impossible for the Brownian motion to visit a prescribed point. Of course, the Brownian motion will visit somewhere, but it won't be the point that you selected in the beginning.
Mhm.
Okay, so the two-dimensional Brownian motion just can't hit points like the origin. However, it's a little bit nuanced, because if you specify any open set, say a very small open ball around the origin, then, and any large time, then there will exist a time at which the Brownian motion will visit that open set. So that we have perpetual return to every open neighborhood in space. Okay.
So can I, so
Yeah,
if
please.
can I say this? So
Yeah.
if we move like a three-dimensional Brownian motion in the universe, so then at some point we cannot come back to the Earth, is it right?
Yeah, exactly. It will leave our solar system, right?
Yeah,
A three-dimensional Brownian motion in space would just leave our solar system eventually, and then never come back.
Now come on, that's
and it would leave our galaxy and never come back.
That's bad.
Yeah, and then so that is, and it's different than dimension 2. Dimension 2 can't hit a point,
Yeah,
but it can hit. It will perpetually return to neighborhoods.
yeah.
That is the distinction.
Yeah, very
So-
interesting. Yes.
Yeah, it's very interesting. Yeah, exactly.
This is because the points in the space, in the two-dimensional, it is measured to be 0. That's the reason.
No, it's not measure 0.
Dimensional one, like
No, it's
measure
not,
zero.
because you can put up a plane, and a plane has measure 0, and it will hit a plane.
Jeremy, what,
yeah.
I guess in that first line of case n equal to,
Yeah.
BT not equal to x, you do mean that the probability of hitting that point is 0?
Yeah, almost. So I say
Not
has
that
the following for almost every omega.
Yeah.
Then you have that.
Yeah, and so it's really not that it will never get there, but that the chance to get there is
Impossible. It's what we could, it's the impossible event, meaning it's a probability 0 event.
yeah.
Exactly. Yeah.
So
But they're
T2
also
is an open set, right? Not just the open set. The last.
you mean for the second part of
open set.
Yeah.
dimension 2. Yeah,
Yeah.
so you specify just any neighborhood, say around any point, and the Brownian motion will keep perpetually returning to that neighborhood.
Mhm.
Exactly.
Yes.
Okay, so dimension 2 is special. It's the in-between dimension. Okay. So now I want to talk about local time. Okay, so this is going to be a one-to-one dimensional. Okay, So this is a one-dimensional Brownian motion. Now, fix a point in space A. You can take it to be 0 if you want. Now define the following random variable. This is 1/2 epsilon. So this is going to infinity as epsilon shrinks, multiplied by the amount of time that the Brownian motion spends in the interval of radius epsilon around the point A. So how much, this is measuring how much time does the Brownian path spend near the point A. So it's keeping track of that. Okay, of course, what we want to do is take epsilon to 0 and ask if it converges to something. Okay, so this measure just is Lebesgue measure, amount of time. So there exists, and this is a theorem, I'm not writing it as a theorem, but it's a textbook theorem. So there exists a continuous process, L, such that the L epsilon converges to this L. Okay, so this L epsilon up here converges as epsilon goes to 0 to something that we call the local time of the Brownian motion at the point A. Now, when A is 0, we're just going to leave off that. Okay, so this is measuring in some way how much time the Brownian motion spends at the point A. All right, so another thing that I want to talk about. So if you take any sample point, so define the 0 set. So this is simply the set of times at which the Brownian motion is 0. So now define a measure. So define var theta as the measure on the positive real line with distribution function given by the local time. In other words, the measure of the interval from S to T is just the change in the Brownian motion. Ordinary sense of a distribution function. You're using the local time as a distribution function. Okay, so then the measure, so here's a theorem, then the measure is almost surely supported on the 0 set. In other words, the set of times at which the Brownian motion visits 0. So what does this mean? That the local time process only increases when the Brownian motion hits 0. Now, if you've taken a real analysis class recently, the way you can think of this is similar to, say, a Cantor set and the Cantor function. If you don't remember that, that's fine. Okay, so the Brownian motion, the local time of the Brownian motion only increases when the Brownian motion hits 0. This sort of makes sense from the construction. It's not a mystery. Okay. So now I want to talk about how do you measure the set of times at which the Brownian motion, the one-dimensional Brownian motion, visits 0. So I'm just going to review Hausdorff measures and Hausdorff dimension. So this is a method by which we can, a formulation for how we can measure the size of sets. Okay. Now fix some number between 0 and 1. Now given a small number delta, so let H denote the following outer measure on the real line. So it's defined as an infimum over all coverings of the set by sets that have diameter less than delta. And then you sum up the diameter of the sets raised to the power p. Okay, so what happens if you take a small number and raise it to a higher power? Then it becomes small, right? You take a small number, you raise it to a power, it becomes smaller. So clearly if you raise p to a higher value, you're making this smaller because delta, you should think of delta as a small number. Okay, so this is a sort of standard sort of construction of how to build outer measures. So the dimension p outer measure on R is defined in the following way. So you just take the limit as delta goes to 0. So here you see delta is a small number. Okay, so this is the Hausdorff outer measure. All right, so it's defined through coverings. All right, so now I'm going to define the Hausdorff dimension. So the Hausdorff dimension of a set is the infimum of the set of P such that you get 0. So we said before that if you take P to be larger, you get a smaller value. Okay, so this is defined as the infimum of P such that you get 0. Okay, little tricky. This takes a little bit to digest, but this is the basic idea for how to define the dimension. Okay. So let me just give a few examples of Hausdorff dimensions. So for instance, when d is equal to 1, if you have an interval, a sub-interval of the real line, of course, it's going to have Hausdorff dimension 1, right? So the real line has dimension 1, and interval isn't so different. So intervals have dimension 1, countable sets, very easy to show that they have Hausdorff dimension 0. A point has Hausdorff dimension 0. You know, a countable number of points still has Hausdorff dimension 0. Okay, how about something a little bit more interesting? So the ternary Cantor set, if you remember the Cantor set from real analysis, that has the Hausdorff dimension, it's log of 2 base 3. So it makes sense that it's base 3 because it's the ternary Cantor set. If you remember, it's cut into thirds. So yeah, okay, so it should be base 3. Yeah. All right, so now here's the interesting thing. So this is a theorem. Now for a Brownian motion, how big is the 0 set? That is the set of times at which the Brownian motion hits 0. So sort of a textbook theorem is that when the Brownian motion does, you know, that it, sorry, I should said in the event, this is just, it almost surely always has Hausdorff dimension 1/2. Okay, so the 0 set almost surely has Hausdorff dimension 1/2. Okay, so it has a non-trivial dimension, has a non-trivial size. So it is a sort of a fractal, like the Cantor set is a fractal. It has a special dimensionality to it. Okay, and you can see in particular that it is not countable. So it is not like a few points at which the Brownian motion hits 0. It is an uncountable set, otherwise it would have Hausdorff dimension 0. It has a non-trivial Hausdorff dimension. Okay, so that is interesting, has a non-trivial size.
Hi, Jeremy, can I have a question?
Yeah, sure, please.
So here for the Brownian motion B, the Hausdorff dimension 1/2.
Yeah.
How about the fractional Brownian motion?
I don't know.
If this Hausdorff dimension related to the memory parameter. Is it related?
I don't know. So I don't know enough about fractional Brownian motion to know, but I'm sure that there's some beautiful result like sort of analogous to this that has some non-trivial, you know, exotic dimensionality to it. Depending on the parameter, you know, on the parameter of the fractional Brownian motion.
I think probably some relationship between this Hausdorff dimension and the memory parameter. Probably they are same. It's interesting. Yeah.
Yeah. Absolutely.
Okay, good. Thanks.
Okay, sure. Okay, so that was a little bit of a summary of what happens in dimension 1. So dimension 1 has the minimal number of degrees of freedom. And you can see it's quite different. We already saw that it's quite different in dimension 2, that the Brownian motion in dimension 2 will not even visit the origin after time 0. It never returns to the origin. So one thing is that its 0 set is trivial. It's empty. Okay, so you already have a trivial set of times at which the Brownian motion visits 0. And yet there's not a local time to study in dimension 2. Okay, so this is a non-starter. There's nothing to study that is analogous to the one-dimensional local time. Okay. All right, so what I want to do is I'm going to talk about a process that that is in dimension 2, that is a pretty natural process that does have a local time. It does have a 0 set that you can study. Okay, now this is going to be constructed from an integral kernel that has appeared in 3 very recent articles. And so in a slightly different form, it appeared about 20 years before in this article by Bertini, by these Italian mathematicians. Okay. All right, so before I construct that integral kernel that has been appearing in these recent articles, so I want to define a special function for you. Okay, so this is not, I don't think this is a widely known function. So that's why I think I need to define it. So define nu in the following way. So it's defined through this integral. So you see that x is the variable. And what do we do? We're dividing by gamma, the gamma function, right? So the shifted gamma function. So some mathematicians refer this to as the Volterra function. Okay, so take a close look at this integral formula. Okay, so looks complicated at first, but actually it's very easy to remember because it resembles the Maclaurin series for the natural exponential function. You know this Maclaurin series for the natural exponential function. Now imagine you just replace the summation by an integral, and then you replace the factorial by a gamma function. Well, then you have the Volterra function. So once you know that, it's very hard to forget. Okay, so one very basic thing about this is it has a Laplace transform given by an elementary function, 1 over s log s. Okay, so that already is a key that it is a very important function. Now, this appears in a very famous formula called the Ramanujan identity. So the Ramanujan identity is that nu is equal to the exponential function minus this little thing right here. So minus nx. Nx is the Ramanujan function. The Ramanujan function has this form, and you'll notice as a statistician that it has looks sort of like a Cauchy distribution, right? But it has log in there. So this is the log Cauchy density. So this is considered to be an ultra heavy tail. So for us, the Ramanujan function is just sort of the Laplace transform of the log Cauchy density. Okay, so that is a very beautiful form. And just to get the basic idea how this function behaves, it is 0 at 0 and it's infinity at infinity. It's increasing. So near 0, it increases quite quickly. So it has an infinite derivative because you can see it's just like 1 over log. Okay, so it increases extremely quickly at near 0. And then at infinity, it is actually just basically the exponential function. Okay, so it's like a type of exponential function. The only thing that I warn you about is that Volterra function, also there are other functions called Volterra functions. So when you do a Google search, you have to be a little careful. Okay, so now I'm going to construct this integral kernel that has come up in literature. Okay, so as before, G just represents the Gaussian function, in this case, dimension 2. And then for a strength parameter lambda and a time t, then we define this integral kernel in this way. So this is equal to, it is a Gaussian in the first part, plus some extra stuff, right? So mainly it is a Gaussian, right? The first term is the Gaussian convolution, just like a 2-dimensional Brownian motion. So that is already familiar from Brownian motion. And then the second part, what do you need to see here? Okay, so it's built out of Gaussian functions, and then it's built out of the Volterra function. That's mainly what you need to remember. Okay, so it's built out of Gaussian and Volterra. Okay, so now, where does this come up? Because this seems like a random formula. Okay, so it does sort of come up from sort of a certain thing in quantum mechanics. It is basically corresponding to a 2-dimensional particle that feels a very singular repulsion at 0. Okay, so only at 0 it feels a repulsive force, but otherwise it is a freely moving particle. Okay, so this corresponds to this Schrodinger Hamiltonian. And so I'm not going to say too much about that because maybe this isn't the most important part, but so this integral kernel is related to this operator h in the following way. So it is exponential of h. No, if you take the integral kernel of that, that is where this f comes from. Okay, so it comes from quantum mechanics in this way. Okay, now this family of operators is a semigroup, just in the sense that you multiply exponentials and the parameter adds. So that means that the corresponding integral kernels should satisfy this identity right here. So this is the semigroup property. Now, this is like a transition density almost, except for a transition probability density, it should have probability 1. Okay, but it is very easy to see from the formula that if you integrate it, you get 1 plus some positive numbers. So these are not probability density functions. Okay, so what I want to do is I'm going to make a probability density function out of them in a sort of trivial way. So I define the following. So remember that the capital F is just you integrate away the second variable y. So you start with a function of 2 variables, you integrate out the second variable, and then you get the capital F. Okay, so define this transition density D in using this formula. Then these are just normalizing factors. If you spend 10 minutes thinking about it, you would think of this also, that all that you need to add is these little factors to make this a transition density function. Okay, so now if you integrate out y, you get 1, and you still have the semigroup property. In other words, the Chapman-Kolmogorov relation. Okay, now this is a consistent family of transition probability density functions for an R2 valued process. Now, if you differentiate in time, in the time parameter little t, then you get this diffusion equation right here. So this is just the Laplacian. So if we didn't have this term, then we would have just the standard Laplacian. And then this term characterizes the drift of the process. Okay, so the drift function is this b right here, and I'm going to describe what the characteristics are. So the corresponding stochastic differential equation is for the process corresponding to this is just, has the diffusive term, which is just driven by Brownian motion, plus this drift, right? So what is the drift doing? So the drift function is pointing towards the origin. So it's pulling the process towards the origin. And so the question is how how large is that drift? Okay, so how much is it pulling? So away from the origin, it basically just vanishes. So it's negligible away from 0. And it blows up near 0 with the following asymptotics. It's 1 over a log of 1 over a. Now, this log of 1 over a actually makes it a little smaller. So because it is acting against the a, right? So this log of 1 over a is making this slightly smaller than what you'd get if you didn't have it. Okay. All right, so let's think about this process. So if you define the radial process R as the norm of the process X, then it satisfies this sort of Bessel equation. Okay, so this is now a one-dimensional stochastic differential equation. It's driven by a Brownian motion, and then it has this extra drift term. This is a standard thing for a Bessel process. Okay, and then it has this drift term, which we already had from up here. Okay, now it is well known that a two-dimensional Bessel process, which is nothing more than the norm of a two-dimensional Brownian motion, it will never go to zero in the same sense that a Brownian motion will never go to zero. So if you didn't have the blue term, this would describe a process that never goes to zero. Okay, now, but you've added the blue term, and the blue term is pointing, it is a drift term pointing towards the origin. Now, you can ask, well, is that drift term enough to make it so that your process will now visit the origin, unlike a two-dimensional Brownian motion? Well, let's recall the size of this drift term pulling towards the origin. Okay, so we have this term right here, but this term is infinitely bigger than this term, right? So this term, this log is in the denominator, so it is making this smaller. Am I not right? Okay, so this is infinitely smaller than this. But it's just playing a perturbative role here. So if you have a process like this that will never visit zero, and you add this term that's basically infinitely smaller around zero, so do you believe that the result will visit zero? So that this turns out to be a very subtle question. So the process, the resulting process, this perturbative term, even though it's infinitely smaller around zero, actually can visit zero. Okay, so I'll say that on the next slide, or the next slide after this in a minute. So first, let me define a few things. Define a sample space of paths and define a coordinate process on that path space that is just evaluated at time t just by plugging in t, and then define a filtration. Okay, so and then define a probability measure on the path space corresponding to an initial position x that just has the transition densities of this corresponding to the d that we defined before. Okay, so we're just defining the path measure corresponding to the transition densities that we defined before. Okay. Okay, now recall that we defined this event O. So this define this as the event that the process will visit zero at some time. Okay, so then proposition, something that we proved, is that there is a positive probability that the process will visit zero, even though we're basically adding a very small drift compared to the drift that would push away. So it's enough to make it so that the process actually visits zero. And if you condition on the event that the process never goes to zero, that it stays away from the origin, that conditional measure is actually just Wiener motion. It's just a Brownian motion. Okay. All right, so now I want to say a little bit about local time. So we now have a process that for some subtle reason, so it can actually visit zero, unlike two-dimensional Brownian motion. Okay, so this opens up the possibility that we study the local time in a similar way that we did before. Remember that the local time for a one-dimensional Brownian motion was a function that only increased when the Brownian motion visits zero. So it's somehow, mostly it is just waiting and pausing, but it increases when the Brownian motion hits zero. Okay, so we're going to define it in this way. All right, so it is this sort of complicated factor here, well, more complicated than before. So it is basically 1 over epsilon squared and then log squared. So we have a log in there. And then this is the amount of time that this process spends within a distance epsilon from the origin. So this is the local time. This is sort of measuring the time that the process spends within a distance epsilon from zero. Okay, So then the theorem is just there exists a limit for this process as epsilon goes to 0. Okay, that is the result. This thing right here converges to something. Okay. All right. So remember that we defined this function that this had this form. It's sort of built out of this capital F function is just built out of a Gaussian and the Volterra function. Then the next theorem just states that the local time has a very fundamental importance to the path measures. In that if you take two strength parameters, lambda prime and lambda, then the path measure depending on lambda prime is absolutely continuous with respect to the path measure with lambda. And then the radon-Nikodym derivative is just, well, it's something that depends on the local time. Okay, so this is telling us that the local time has a fundamental role in defining these path measures. Okay, all right, so last little thing. So now I want to talk about the set of times at which the process visits 0. Do you remember before it was sort of a fractal set that had dimension 1/2 in the dimension 1 for a dimension 1 Brownian motion? Okay, so what about for this process? What dimension do you think it'll have? Okay, so the following is true. So this set of times at which the process visits 0 is uncountable in the event that the process does visit 0. So if the process visits 0, it will visit 0 uncountably many times. And again, going back to Marshall's point with probability 1, the probability 1 event. Okay, so next, it's a small set. It has Hausdorff dimension 0. So Hausdorff dimension is not a good way to measure this set. It's too small. Okay, and then the third point is just what we said before, that the local time only increases when the process visits 0. Okay. All right, so how do we measure a set with Hausdorff dimension 0? We need a more refined sort of formalism. Okay, so basically it's a sort of analogous thing involving logarithms. So we define this function d that instead of having a power function like we did before, we have something that depends on log, and so it's basically a power function of the log function. And you will notice that this function is bigger than any power function. So if you take a to 0, then this will be bigger than a power function. Why? Because it involves log. Okay, so then we define an outer measure using a very analogous formalism to what we had before. It's just that instead of having power functions right here, we have these more interesting things involving logarithms, powers of log. Okay, so this is same. So we just take infimum over all coverings of the set, and then we plug in the diameters of the set into this special log function. Okay. All right, so then all right, so in a little bit of lingo, so if we have a Hausdorff dimension set, 0 set, so let us refer to S as having log Hausdorff exponent H, if H, this fancy H, is the infimum such that this is 0. So this is just analogous to the other slide that we had before. It's just using these new functions involving log rather than powers. Okay, so then the statement is that for almost every omega, in the event that the process does hit 0, if it does hit 0, so in other words, if this talks about the case where you do visit 0, then this set, the set of times at which the process visits 0, has log Hausdorff exponent 1. So it has a non-trivial exponent. So you can really characterize the size of these sets using this formalism. Okay, so you can go beyond just saying that it has Hausdorff dimension 0, and you can go a little deeper and sort of use logarithmic dimension functions to characterize the size of the set. Okay, so now I just want to summarize what we did. Okay, so first we just reviewed the definition of Brownian motion and discussed some of its behavior that depends on the dimensionality of the Brownian motion. So in particular, we discussed in the case of dimension 1, we discussed the local time and its 0 set. That is the set of times at which it visits 0. And we sort of made the point that we don't really have an analog of this, the local time or the 0 set that is interesting in dimension 2. There's just no theory to, there's nothing to work with there. Okay, the Brownian, a 2-dimensional Brownian motion just doesn't visit 0, so you can't build a theory on that. Okay, then starting with an integral kernel that has arisen in several articles, especially in the last few years, we constructed an transition density function, and that allows us to talk about a certain 2-dimensional diffusion that has some exotic behavior that we saw. Okay, so in particular, we discussed the local time and the 0 set for that. Okay. And that is what I wanted to say. So if there are any last questions.
Seems quiet today. Is there anybody with a question?
I think it's good work. It's good. Yeah.
Yeah, I think it's interesting. We've enjoyed working on this, and we've learned a lot about it.
Yeah. So have you submitted this work somewhere?
We're trying to finish up in the next, I guess by the end of the semester would be great.